what we were just talking about the last time, which is oxidation and reduction, right? The transfer of electrons. That's something that you've been seeing happening all semester long. So really, I took you through some formal analysis showing you how to balance these reactions by following the electrons that are being transferred, okay? So that's a skill that I'm hoping that you're going to learn. Actually, it's a skill that you probably already had, right? We've been working on it all semester long. But you are expected to recognize when something's being reduced and when something's being oxidized. And now to understand that this happens together, okay? And just to refresh your memory, like on this bottom reaction, where I show you the whole thing, right? This is an oxidation reduction reaction. But you also know how to recognize these as we've been using classifications like double replacement, single replacement, combination. Let's do 1 for single replacement, 2 for double replacement, 3 for combination, and 4 for decomposition. All right. This reaction down below with the iron and palladium nitrate, is that 1, 2, 3, or 4? Let's see a show of hands. What classification of reaction is this? Take a moment to think about it, nice and high. 2, 3. Right. This is correct. It's 1. It's a single replacement reaction, right? Where we have usually a metal and an ionic compound, and the metal becomes oxidized or reduced and then swaps places with the cation or anion in the compound. So now you have a little bit more insight. Single replacements, why are they swapping around? Why do these things happen? Well, a lot of that why you won't be answering until you get to second semester, okay? But in this case, oxidation and reduction, that's what's actually driving this reaction. It's the reduction that's actually driving this reaction. But right now in Gen Chem 1, I'm just showing this to you essentially for the first time. So the expectation is that you know how to recognize these. What's being oxidized, what's being reduced, what kind of reaction do we classify this as, and how to balance the reaction first and foremost, right? But we can classify this a number of ways. We can call it a single replacement. We can call it a reduction oxidation, right? A lot of these labels that we assign, we have multiple labels that we can use for any given reaction that we might be describing. All right, so now we're going to talk about reduction and oxidation, but in a slightly different sense, especially as you go on. I already know most of you are biology or chemistry majors. You told me that by a raise of hand earlier. So most of you are going to be going on to biochemistry classes or molecular biology classes and whatnot. And you're still going to be using these terms, reduction and oxidation, but they're not going to be ionic compounds. They're not going to be an exchange of electrons to form cations and anions, but it's still oxidation and reduction. You may recall I gave you those other definitions up here about up in the upper left. Oxidation, it's not just the loss of electrons, but it's also gaining oxygen or losing hydrogen. That's also oxidation. Reduction, it's not just the gain of electrons, it's also losing oxygen or gaining hydrogen. In doing so, atoms are also becoming reduced. So let's take a closer look at that today, all right? Here's a classic, okay, what kind of reaction is this? It's not single replacement, it's not double replacement, but what other kind of reaction is this? It's combustion, but how else might we classify this? This is also redox, that's right. Combustion reactions are also redox, and let me show that to you. Even though none of these are ionic compounds, so we're not forming cations and anions. But take a look at those earlier definitions I told you about. If you're gaining oxygen, you're becoming oxidized. Well, look at the reactants and look at the products. What element is gaining oxygen? The carbon, what about the hydrogen? Is the hydrogen gaining oxygen? Yeah, they're both gaining oxygen. Both the carbon and the hydrogen in methane are being oxidized. Let me just show that to you for the carbon, okay? Here, the carbon is being oxidized. Okay, this is losing hydrogen and it's gaining oxygen. Here, let's just write, it gains oxygen and it loses hydrogen. Both of those are definitions of being oxidized. Is this balanced? No, this is not balanced. But why don't we balance that first? That's a good point. I should always balance these things first. Okay. There's a 2 here, and there's a 2 here. What's being reduced? Yes, oxygen's being reduced. Thank you. Yes, of course. Something has to be reduced. Okay. If carbon's being oxidized, the only thing that's left is the oxygen. That has to be reduced. But let's take a look formally at how we would find this, right? This is being reduced. You can also think of it as being reduced. Here, the oxygen is gaining hydrogen, right? And that was one of the other definitions I gave you. All right, but the formal way to show this, though, is using something that's called oxidation numbers. We have oxidation states and we have oxidation numbers. In oxidation state, that would be what we've been doing all semester long. If we have sodium and sodium loses an electron, what's the charge? 1+, right? So that's the oxidation state. Sodium would be 1+. Chlorine picks up 1 electron, right? When they form ions, that's the oxidation state. Now we're going to think about these atoms as they're not gaining and losing electrons, but they are going to be redistributing their electron density. Remember electronegativity and how oxygen and fluorine and nitrogen are very, very electronegative? So they have a much stronger attraction for those shared electrons in covalent bonds. Remember that? Okay. So let's take a look at what's happening here with the carbon. Let's take a look down here at the lower left, all right? The carbon in methane. Carbon, it turns out, is more electronegative than hydrogen is. So if I were to draw the dipole moments, I know the eyes, I can see the eyes rolling in the back of your head right now. The dipole moments on these bonds, right? The delta negative is towards the carbon. So carbon's going to have a little bit more of that electron density around it versus where the hydrogens are. So we can think of that as carbon is kind of gaining the electrons, but it's not completely gaining them like it would if it were forming an anion. It's just getting a little bit more of the electron density there. If we take a look at carbon dioxide, oxygen is very electronegative, much more electronegative than carbon. And we have 2 of them, and they're double bonded, okay? So in carbon dioxide, those oxygens have a much greater share of that electron distribution around the oxygens than it does around the carbon. So that carbon then is a little bit more positive than it would normally be if it was by itself in nature. All right, so that one's going to be a little bit oxidized. The more oxygens you attach by covalent bonds to an element, to an atom, right? The more oxidized that atom becomes. It's not losing electrons, but it's losing the electron density. So let's write that down. So this is an incovalent molecules, right? The electrons are not lost and shared, lost and gained, sorry. But the distribution, the electron density distribution is changing. Now there's a formal way that we can actually track this. And on the next slide, there's a list of rules that you can follow to track these oxidation numbers. I'm going to try to simplify that for you, okay? If you have a hydrogen or an oxygen in your covalently bonded molecule, we're going to just assume that it will have the full charge that it would have if it formed an ion, okay? So for hydrogen and oxygen, we're going to assume full ionic charge. So if hydrogen loses an electron completely and forms the hydrogen ion, what's the charge of the hydrogen ion? +1, right? So that's going to be H plus. And if oxygen gains electrons to become isoelectronic with its nearest noble gas in forming an anion, the oxide anion, what's the charge on that? 2-. Now, that's not what's happening here. These are not ionic compounds. These are covalent compounds. So the oxygens in here aren't the 2- oxide ions in a covalent bond, okay? But let's pretend that it is. Same is true for the hydrogen, okay? So if all of these hydrogens, if they all have a 1+ charge, and methane, you're presented as methane, it's neutral. If you look at the molecular equation, it's neutral. So what must the charge be? If the carbon was an ion, what would the charge be? It would be what? 4-. Maybe I should put that in a different color so you can see, because this is all red. It would be 4-. Now it's not 4-. It's not an ion, okay? But the carbon in methane has an oxidation state of 4-. It is relatively reduced compared to what it might be in other materials. Like, for example, carbon dioxide. What would the oxidation number of carbon be in carbon dioxide? Here, let's see if you can just do it. Okay, the answer is 4. All right, it's +4. Let's take a look at that. The oxygens, as I told you, right, we assume that the oxygen has a full 2- charge. So that would be a 2- here and a 2- here. If carbon dioxide is neutral, then the oxidation state for carbon must be 4+. Okay, so here we have, these are not, sorry, I said oxidation state, the oxidation numbers. We get them confused, and I'm not going to have you distinguish between one or the other. The terms are so similar, all right? I don't care about you knowing those terms, but you should know how to address what the number would be on an atom when it's in a covalent compound, not in an ionic compound, right? This is the oxidation number. It's telling you that the carbon that's in methane, that's relatively more reduced than it is when it's in carbon dioxide. You're not taking electrons away, but in a sense you are. You're changing the electron density around the carbon. There's more electron density around the carbon in methane than there is around carbon dioxide. All right, it's very useful because it helps you to explain lots of additional chemical reactions that occur, because they're all occurring due to things becoming more stable as the product. And that has a lot to do with either gaining or losing electrons, or now in this case, changing the electron density. So let me give you a couple more rules on that, and then we'll practice this a little bit. So I'm not going to go through this line by line. The one that I just told you about was number 4 and 5. Okay, oxygens, if you have an oxygen, we're going to assume that that's a 2-, and if you have a hydrogen, we're going to assume that's a 1+. There are exceptions, right? I'm not going to focus on the exceptions. I want to focus on what normally happens here. If you want to know about the exceptions, go ahead and read about them. And if you're curious, you can come by office hours. We can talk about it some more. But 1, 2, and 3, this is no different from what we've been doing all semester long. If it's on a different element, you should assume that it takes on the charge of that element if it becomes an ion. All right, so first of all, if it's pure, and I told you this already, when things are pure, found in their natural state, they're always neutral. So there, the oxidation number is 0. If you have an individual atom and you want to know what its oxidation number is, it's just going to be the same number as you would have if it was an ion. So chlorine, for example, would have a 1-. Fluorine would also have a 1 minus, but since fluorine is the most electronegative atom that there is, it will always be. You can assume fluorine is always a 1 minus, just like we can assume oxygen is a 2 minus and hydrogen is a 1 plus. Okay, and these last two are very straightforward. If it's a neutral compound, the oxidation numbers have to add up to 0. If it's not a neutral compound and it's a covalently bonded molecule, well, that's what a polyatomic ion is, right? A polyatomic ion is a covalently bonded molecule that has more or fewer electrons than it has total number of protons in it. So we just need to make sure that if we're doing this for a polyatomic ion, that the overall numbers add up to whatever the total net charge on the ion is, right? They're the same things. And let me just show you that by way of example. In fact, let's just start this because I just told you that one. Let's just start with the nitrate ion here. We'll go right to left. Here's the nitrate polyatomic ion. We're told that it is a net 1 minus charge. Now, a few chapters ago, we learned how to do the Lewis structure on the nitrate ion. We're not going to go through the Lewis structure for this, and you don't need to for this. You just need to know what the connectivity is, what the skeleton connections are when you start building your Lewis structure. You may recall that that's going to be nitrogen in the middle with spokes on a wheel. We're not going to place all the valence electrons now. We're just looking at the connections. Overall, this has a net 1 minus charge. So what's the oxidation number on nitrogen? Why don't you work it out for a second? Don't blurt out the answer. Just work it out using the simple rules that we just talked about. And is it going to be a positive number or a negative number? If it's positive, raise your hand. If it's negative, raise your hand. Okay. Everyone who said positive, put your hands back up. How many positive charges are there? That's correct. It's 5. 5 positive charges. Let's take a look at this. The oxygens, they each have a 2 minus. So that's a total of 6 minus charges. This needs to total out to be -1. Therefore, the oxidation state of nitrogen must be 5 plus. Now, it's not a 5 plus ion, okay? But if you look at the electron distribution, it's mostly being sucked away from the nitrogen onto those more electronegative oxygens. So it's really a relative number. It's not an absolute, okay? It's a relative 5 plus. That's the oxidation number for nitrogen in the nitrate ion. Let's look at what it is in these other molecules. Now here you're shown in 3 dimensions, all right? I just took this. This is one of the problems in the back of the chapter. This is N2O5, dinitrogen pentoxide, all right? Blue is for nitrogen, red is for oxygen, okay? Let's show what those connections are. Let me just translate this for you. Okay, that's just taking the 3D and showing it in Lewis structure format. Here's N2O4, dinitrogen tetroxide. Okay, that's why we learned the nomenclature rules, because when you mix nitrogen and oxygen together, you get all sorts of different compounds that differ in their ratio of nitrogen to oxygen in the compounds. Here's just 2 examples, okay? But let's look at what the oxidation state is for nitrogen in these different materials. Now you can do these a number of different ways. First, let's just assign the oxidation numbers for oxygen, because we're going to assume that's always what you find for oxygen when it forms the oxide ion. So these are all 2 minus. Okay? 2 minus, 2 minus, 2 minus, 2 minus. These are all, or both of them, are presented as neutral. So if we have on dinitrogen pentoxide on the left, we have a total of 10 negative charges, which means the positive charges have to be positive 10. And that has to go on the 2 nitrogens that remain. This is very symmetrical, so we're just going to split them up. It's going to be +5 on one and +5 on the other. that gives us overall net neutral. So the oxidation state, or the oxidation number for nitrogen in dinitrogen pentoxide is the same as what we would find it in the nitrate ion. But what about N2O4? What's the oxidation number on nitrogen in N2O4? It's 4+, right? It's the same process, because now the negative charges total up to 8. We have to split that in two. This is a symmetrical molecule. Okay? It's really no more tricky than this. But it's a way to identify that in these different molecules, nitrogen will behave differently because its oxidation state is different. Okay? Just like when you go and study glucose metabolism and all the reactions in biochemistry that take glucose and turn it into energy for you. You're doing a number of different reactions that are oxidizing glucose down to smaller molecules. And every time you're doing that, you're changing the electron density around the carbons in glucose until finally, who remembers what you put out at the end after you metabolized all your sugar? Carbon dioxide, okay? Carbon dioxide. Take a look at this, what I did you up here, right? Carbon in methane, you can't get more reduced than that, all right? We have all the hydrogens that carbon can accept, and there's no oxygens on it. So that's carbon in its most reduced form, where it would have an oxidation number of 4-. Here, carbon is most reduced. And in carbon dioxide, as carbon with an oxidation state of 4+, this is carbon in its most oxidized state. That's just a little for your information. All right, let's do some more practice with this. Let's do this with some other molecules. Here's a series of oxo acids. I think I showed you these in the nomenclature part where we built, you can name these hypochlorous acid, chlorous acid, chloric acid, and perchloric acid. We're not going to go over those names again, but let's just focus on the relative oxidation state of the chlorine now in these different molecules. Because you can see on the right, I've drawn the structures out for you on the right. Here's the molecular formula on the left. And we can see that as we add more oxygens to the chlorine, we're going to expect what about the chlorine? What's going to happen to the chlorine? Is it going to be more oxidized or more reduced? It's going to be more oxidized because we're putting more oxygens on it. And you can show that by following the oxidation numbers. So let's stay in red for these. So oxygens are always 2-. The hydrogens are always 1+. So you just total them up, and whatever's left over, since these are all neutral, is going to be whatever the oxidation number is on the chlorine. So what is it up here for? This is chlorous acid. Here, I'll even write these in here for you. This is hyperchlorous acid, chlorous acid, chloric acid, and perchloric acid. Okay, so what did you say the chlorine was? Actually, let's start at the top. Let's go for hyperchlorous acid. What's the oxidation number on the chlorine here? 2- and 1+. So it's got to be +1, right? That's the only way that this balances out to neutral. What is it on chlorous acid? 3+, because it all adds up to 0. And I think you kind of get the trend here, 5+ and 7+. See what's happening? As we're adding more and more oxygens, we're effectively oxidizing that chlorine. But chlorine doesn't exist as, I mean, think about how we studied gaining and losing electrons earlier in the semester. Chlorine is all the way over there on the right-hand side. it only needs to gain one more electron to become most stable. It's not going to lose 7 electrons to become most stable because now it's isoelectronic with neon. It doesn't do that. It's far, far easier for it to gain 1 than it is to lose 7. But in the context of this molecule, it's effectively losing 7 electrons. It's not really, but it's effectively losing, not on its own. It has no choice because it's bonded, it's covalently bonded to much more electronegative oxygen that has a much stronger attraction for those shared electrons than the chlorine does. The same is true for the carbon that I showed you before. Here, I have some more examples here for us to practice with. Let's move these down here. Let's take a closer look at the carbons again. Here's the methane, once again, on the left-hand side. So we already know that that's 4 minus. And here's carbon dioxide. We already know that that's 4 plus. Okay? Those are the two extremes. But if you go back to where carbon is on the periodic table, when carbon doesn't lose or gain electrons, it's right there in the middle. It's in group 4. So it's going to share its electrons. But we know that that sharing is not equal. It's an unequal sharing. And now we're describing that by the different oxidation numbers that we would assign for carbon in different molecules. But at its extreme, in methane, carbon's going to gain 4 electrons, as if in the middle of the periodic table, it gains 4 electrons to be isoelectronic with its nearest noble gas, in this case, building up to look like neon. But it's right in the middle. It could have just as easily lost 4 electrons and be isoelectronic with helium. Okay, it doesn't do that, but in the context of these molecules, it kind of does. It's just the electron density. Okay, we don't need to spend a lot of time going through all of these. I'll just show you a few. The R here, R group, this just means that it contains carbon. It's without having to draw the rest of the molecule. So here's an R group and another R group. Typically, when you have R groups, typically with R groups, we assume that the oxidation numbers net out to 0. So just for the sake of demonstration, these are all going to be 0. I won't challenge you with these on an exam, so don't worry about that. I just wanted to show you a general trend here before we do some practicing. Right, the carbon this is an aldehyde. You'll learn all this stuff coming up in organic chemistry. This is an aldehyde. This is a ketone. This is a carboxylic acid, but you've seen those in Gen Chem 1. We've worked with acetic acid, right? Carboxylic acid. Look at what's happening to the carbons here. In this case, we've got 2 minus, 1 plus. So this carbon on the aldehyde has an oxidation number of what? 1 plus. In the ketone, it has an oxidation number of 2 plus. In the carboxylic acid, and that's a plus, so it's 3 plus, that's right. All the way till you get to carbon dioxide, that's the most it can get, okay? So, and look what's happening here. We're replacing these numbers, but as we're adding oxygen or taking hydrogens away, we're oxidizing the carbon. You'll see that? All right, let's do some practicing here. Let's look at the oxidation number on sulfur in the sulfate polyatomic ion, when it's in sulfur trioxide, and when it's in sulfur dioxide. Why don't you have a go with those? Now you're going to have to draw out the skeleton structure. It's like building the Lewis structure. But remember, spokes on a wheel, or if it's linear, you want it symmetrical, or you want the least electronegative atom in the middle. Spokes on a wheel. Spokes on a wheel. This one's just going to have sulfur in the middle. Right? You don't need to memorize the electronegativity scale to remember that oxygen, fluorine, and nitrogen are the most electronegative. So when you've got them with anything else, the anything else will almost certainly be in the center. All right, so let's assign oxidation numbers here. 2- all around. So what's the oxidation number on sulfur in the sulfate polyatomic ion? Plus 6, because it has to net out to 2-. Okay. I didn't mean to intentionally fool you here. I should have drawn this like this. Okay. What is it on sulfur trioxide? It's also plus 6. How about sulfur dioxide? Plus 4. Okay, you can do this. Is sulfur losing 6 electrons to become isoelectronic with what? What would sulfur be isoelectronic with if it lost 6 electrons? Neon. Is it doing that? No. Okay. But in this combination with electronegative oxygen, it effectively is. All right, let's do it with a series with carbon. Carbon monoxide, carbon dioxide, and the carbonate ion. You already know what it is in carbon dioxide. But this time I won't fool you. All right, 2- for all the oxygens. So the oxidation number on carbon and carbon monoxide is 2+. Carbon dioxide, it's 4+. And in the carbonate ion, it is 4+ again, because it has to net out to 2-. Okay? Just keep in mind that when you have other materials in there that aren't carbon or hydrogen, then you assume that the oxidation number on that atom is what you would normally have if it formed an ion.